Okay, great. Thank you so much. What a great day. Good day to everyone. I'm here to speak on behalf of benthic current dominated depositional systems, also called conturite depositional systems, and to give an integrated picture of this end member, especially at the log, outcrop, and core scale. I will also point out the key influences on mixed systems and some specific recognition criteria. First, we'll say a very few words about deepwater benthic currents, their wide variety and widespread distribution and effects on sediments, as we've heard. The bottom line of this part is that such currents are everywhere, and what would be weird is if such currents were absent. And Professor Schieber just showed us a bunch of the evidence in the rock record. Next, we'll discuss the depositional systems associated with those benthic currents, their characteristics and recognition criteria, as well as their relation to mixed systems, with the bottom line here that they are variable but distinctly different from deep water fans. Benthic currents are one of three main modes of sediment delivery to deep water systems, the others being sediment gravity flows and direct settling from suspension. The information in this talk comes from both the modern and the ancient. In the modern oceans, we have extensive current measurements as well as observations of more than 260 sediment bodies associated with benthic currents, shown in tan and numbered on this map. In the ancient, we have more than 42 examples from 26 basins across all continents of Permian to Pleistocene ages so far. Now, there has been a fair bit of work on the oceanographic processes associated with conturite depositional systems, as Dr. Garcia presented earlier. However, as to the products of those processes, especially vertical and lateral successions in the rock record at the well log and core scale, not so much. Despite some good work on their appearance in 2D views of the seafloor and multi-channel seismic data, proposed facies models and outcrop examples are still warmly debated, and that's kind of why we're here today. And I look forward to hearing especially what Professor Hernandez Molina has to say in the second half. What's new in this talk is a proposed set of integrated recognition criteria from seismic through well log to core, outcrop, and thin section. Here's where that integrated approach leads. These systems are the result of frequently repeated episodes lasting hours to months of high speed but subcritical traction currents flowing along slope. They contain a wide variety of sedimentary features. They are distinctly different from deep water fan systems, which are dominated by downslope, frequently supercritical sediment gravity flows. Of course, Mother Nature doesn't always cooperate with our neat categories, but in general, we can consider conturite depositional systems and deep water fans as end members of a spectrum of mixed deep water systems, marked by various degrees and timings of interactions of along slope and downslope currents. Conturite depositional systems are themselves variable to some degree, but distinct from those systems formed by episodic downslope flow. Those distinct differences arise from the characteristics of deepwater benthic currents, which we will now discuss for a moment. The floor of the ocean beyond the continental shelf is affected by many types of currents. These currents include thermohaline-induced geostrophic benthic currents, of which contour currents are only one type, denser water eddies, internal waves and tides, solitons, benthic storms, and tsunami-induced currents. All these current types share the fact that they are driven by gravity working on water masses of different densities due mostly to temperature and salinity. The ubiquity and variety of benthic currents was well summarized by Walter Munk back in the 1980s, one of the grandparents of physical oceanography, who said, "No one has ever reported an interior calm in the ocean." Deepwater benthic currents are present throughout the world ocean, as shown in shades of blue on this compilation by Thran et al. The most energetic bottom currents occur mainly in three settings: along the western boundaries of ocean basins, near sites of deep water formation, mostly at high latitudes and from the Mediterranean, and in areas that are tightly constricted by topography. So with that very short introduction to the key processes, let us now discuss their products. Benthic currents redistribute mud and sand that is delivered downslope by sediment gravity flows, mostly. Benthic currents form a wide variety of erosional and depositional sedimentary features and bed forms at the mesoscale, as well summarized by Robesco and Stowe and that crowd. And we'll hear more about this from the other panelists. At the macro scale, benthic current depositional systems construct substantial sedimentary bodies that are elongated generally parallel to the continental slope. These systems are widespread, with more than 260 separate sedimentary bodies identified, shown here in tan, and they cover about 13% of the seafloor. They are most common off east coasts, formed under the influence of western boundary undercurrents. Seismic to core scale integrated analysis reveals that contorite depositional systems comprise two main geomorphic elements with distinct facies: a contorite drift, which is the main sedimentary body, and a contorite channel or moat, typically found slopeward of the drift. These two main geomorphic elements each have characteristic seismic, well log, and physical and biogenic attributes. The two main elements also have characteristic lateral and vertical stratal stacking patterns, as summarized here. We will discuss each in turn. A contorite drift is the larger volume, typically finer grained part of a contorite depositional system that occurs basinward of its associated contorite channel. The map view example is from the North Atlantic, and the profile example is from the Caspian Sea, which is a lake, by the way, so you don't need salt to make a contorite system. Kind of following up with what Jürgen showed us about the effect of salinity on flocculation. Drifts range in shape from thin tabular sheets, discontinuous to continuous, to mounds at the multi-kilometer scale. These morphologies are also expressed at the tens of meters scale, shown here in outcrop in onshore Angola. Tabular at the base, mounded in the middle, and overlain, in this case, across a nonconformity by a fan channel. In core, we see that no sedimentary structures are unique to this setting. It shares many attributes with sediment gravity deepwater systems. However, contorite depositional systems are dominated by evidence of persistent and frequently recurrent traction transport, cross-bedding, small and larger scale, scours, and lags. And these are the key recognition criteria, along with common to abundant deepwater euryhaline body fossils. As with all other depositional environments, it's essential to place one's detailed observations into their overall stratigraphic and geomorphic paleogeographic context for the most robust interpretation. So in detail, the drift can be divided into three subfacies based on their proximity to the contorite channel. Distal drift facies accumulate farthest from the contorite channel. They're typically fine-grained argillaceous siliceous with very sparse glauconite. It is mostly bioturbated with sparse discrete deposit feeding and dwelling traces. This facies has an overall mottled appearance. Much of the original bedding is recorded only as diffuse bands of different colors with indistinct contrast. Ooh, isn't that interesting? Where did my pictures go? Oh well, feature. Preserved sedimentary structures include sharp-based fossil lags, as well as the very sparse millimeter scale planar and graded beds. Biogenic content is mostly planktonic microfossils, along with some transported fragments of shallow water forms and fragments of deep water thin-walled bivalves. Closer to the contorite channel, the medial drift facies is characterized by mixed grain sizes and lithologies, as well as faster sediment accumulation. This facies comprises calcareous sandy mudstone and siliceous argillaceous muddy sandstone with a few brown glauconite grains and organic matter-rich argillaceous pellets. Primary sedimentary structures and discrete trace fossils are more commonly preserved than in the distal drift. Traces are mostly deposit feeding and dwelling, with some locomotion traces. Sedimentary structures include scours, lags of coarser grains and fossil fragments, current ripples, starved current ripples, and millimeter scale planar and graded beds. Fossil assemblages are similar to those in the distal drift deposits. The proximal drift facies accumulates yet more quickly in the area of a drift that is closest to the conturite channel. This facies comprises various compositions and a wide variety of grain sizes: argillaceous, calcareous, siliceous, and bioclastic mudstone, sandy mudstone, muddy sandstone, and sandstone. Glauconite pellets can constitute as much as 10% of the sand size fraction. Decimeter scale bigradational or conturite sequences are characteristic of this facies. More about these in a moment. Burrows include discrete deposit feeding, dwelling, and locomotion traces. The mudstones are burrowed, but the sandstones preserve many primary structures, including scours, starved current ripples, lenticular and flosser bedding, planar and wavy bedding, and muddy rip-up clasts. Fossil assemblages are similar to those in the medial drift facies, with the addition of fragments of larger benthic organisms such as crustaceans and echinoderms. When we rack up all these criteria, we see that they are differences that make a difference. Now, I'm sure you're thinking that's all very fine, but where are the conturites? But strictly speaking, conturites are these cute little decimeter scale stratal successions that gradationally coarsen, then fine upward, also known as bigradational sequences. Conturites have been viewed as conceptually analogous to the Baumas turbidite sequence. Conturites superficially resemble hyperpycnites in their bigradational grain size profile, but differ from them in the character of bed context, type and abundance of preserved primary sedimentary structures, content of land plant debris, and trace fossil types, abundance, and diversity. The reason I have not stressed conturites is because conturite sequences are not found throughout all conturite depositional systems. It turns out they are most common in the proximal drift facies and not common in nor characteristic of coarser grain conturite depositional systems. Now onto the other geomorphic element, conturite channels and their fill. These channels are elongate erosional depressions on the slopeward margin of a conturite drift. They can be relatively straight and oriented along slope, or sinuous and oriented oblique to the slope. They are characterized by the presence of truncated seismic reflections at their base. Within these channels, sediment moves under the influence of unsteady benthic currents and overflows onto the adjacent conturite drift. As with the drift facies, channel fills have pervasive evidence of traction transport under episodic but frequently recurrent higher energy episodes. In contrast with the drift facies, however, these strata thin and fine upward over the multi-meter scale, and biotubation increases upward with significant burrowing only in the uppermost channel fill. The channel fill facies is characterized by scours, rip-ups, lags, unidirectional crossbeds that thin upward as shown in D and G, flosser beds and mud drapes in A, B, and C, wavy bedding in H, sigmoidal crossbedding and reactivation surfaces in D, I, and J, mudstone rip-up clasts in E and F, along with macrofossil fragments of benthic and planktonic shelfal and abyssal taxa, and low diversity burrows, mostly deposit feeders, and bioturbation increases upward. When we put all these subfacies together, we see that they are indeed distinctly different and stack in a recurrent pattern. A complete succession comprises a relatively thick lower interval that coarsens upward, overlain by a thinner interval that fines upward, all at the scale of many meters, and not at the decimeter scale of a wee conturite bedset. The lower coarsening upward interval records accumulation in the drift part of a system. Across a sharp, generally erosional surface, the upper fining upward interval records accumulation in the associated channel. And these subfacies show up rather clearly on well logs, at least on total and spectral gamma logs. Conceptually, this is how the vertical succession records the oblique lateral migration of the conturite drift and associated channel, from the initial accumulation of a distal drift through the medial and proximal drift to the channel fill facies. So this vertical succession represents the fundamental depositional motif, the building block at the parasequence scale. Their thicknesses in this case range from 1.8 to 7 meters and average about 3 meters. And they can be correlated for many tens of meters along slope and tens of kilometers cross slope. These building blocks stack in systematic patterns, typically progradational to aggradational, as shown on this well log, to record the long-term accumulation of a benthic current-dominated depositional system. So there you have it, the N-member chondrite depositional system, and we'll hear more about recognition criteria from panelists in the second half. We can now consider how to differentiate them from the other deep water depositional systems, starting at the other end of the spectrum, deep water fans. In general, chondrite depositional systems are characterized by subcritical traction transport in relatively clear water under frequently recurring persistent currents that flow mostly along slope. In contrast, N-member deep water fans are dominated by sediment gravity transport under episodic short-lived supercritical currents that flow mostly downslope. For recognition in the straddle record, chondrite systems are characterized by pervasive bioturbation and an asymmetric cross-section with straddle continuity oriented mostly along slope and basinward. Seismic reflection patterns are relatively uniform and thin gradually by downlap, and their spatial extent is generally greater than many deep water fans. Of course, chondrite systems represent one end member of a spectrum of deep water systems that record various degrees and timing of interactions of along slope and downslope currents. And I look forward to hearing much more on how to recognize where one is on the spectrum throughout this session. What does occur to me, however, is that the essential differences among these systems relate to both the relative abundance of along slope clear water traction transport versus downslope sediment gravity flow sedimentary features, and to their 3D distribution. Now, there are reasonably robust recognition criteria at the system scale: the geometry and distribution of levees and lobes, the geometry of the drifts, the migration direction of channel scours and fills, and the geometry and relative size of associated channels. Now, how these translate down to the well log, core, and thin section scale is what we need more work on. So, in conclusion, you will be happy to hear, the essential attribute for the recognition of chondrite depositional system facies is the pervasive influence of persistent along slope benthic currents and subcritical traction transport in a deep water setting. As for mixed systems, well, most I can tell you is what would be weird is not seeing the influence of benthic currents in deep water settings. And we will hear more about mixed systems from Drs. Rodriguez and Serrier after the break. That was a lot to cover in a short time. Let me bottom line it for you. Chondrites do not tell you everything you need to know about chondrite depositional systems, just as turbidites do not tell you everything you need to know about deep water fans. Or rather, chondrites are to chondrite depositional systems as turbidites are to deep water fans, potentially common in some parts, but not the whole story. If you happen to have missed any of that, we have written most of it down in SCBM's Handbook of Siliciclastic Facies in chapters 8 and 9, and in AAPG Memoir 126. We thank our colleagues and collaborators for sharing their insights with us, all the authors of the most excellent publications from which we drew our examples, Drs. Emma, Fabian, Lillian, and Stan for organizing this meeting, and you for your very kind attention. I look forward to your questions and a very lively session. Thank you. And now a word from our sponsors. So coming up in 11 days, the Gulf Coast section of SCPM will be hosting a 3-day conference in Houston in memory of Peter Vail, Bob Weimer, and Larry Sloss, sort of talking about where sequence stratigraphy and how we got to where we are. It's a chance to hear the old guys talk one last time so you can hear a little bit about how the sausage was made. And we encourage you to join us. Thanks.
Thanks, Kevin. That was a fantastic talk. We do have some time for questions. Let's do maybe 5 minutes of questions before jumping into the break. There's some questions that got posted here. I'm going to read one out unless anybody wants to unmute themselves and read it. One was here from Tim Demko. Shouldn't we have different facies models for moats, in parentheses, long linear hydraulic jumps versus channels, dominantly uni or bidirectional flow? Because they may have similar geometries and maybe even geomorphologies, but different products.
I think that's exactly right. The products, because the reason I emphasize channels is moats are, as I've seen them, they're pretty much an erosional feature, and sort of in the way I was talking about them. Essentially, once they start become depositional, once the sediment starts to accumulate in them, they're effectively a channel. So but that's definitely an open question, is how those scour lens shaped cross section features fill in, whether it's from one end with the traction transport going across there, or is it some other processes, some of the supercritical sediment gravity flows and whatever else. So definitely an open question.
Okay. Yeah, no, that's excellent. There's another talk from Morgan Sullivan. I guess he's asking why a contourite channel and not a turbidite channel. The fill looks like a classic turbidite channel, and seismically might be expressed that way too. I guess, do you have any thoughts on, some of the differences internally and maybe geometric apart from orientation between turbidite channels and these contourite channels?
Right. So if we can see the rocks, what we'd see in the contourite or the benthic current dominated ones are traction transport. We won't be seeing all the supercritical turbidites, et cetera, et cetera, et cetera. Whereas, in terms of from the seismic scale, that's going to be a lot more challenging, and that's going to require the larger scale regional context, I think. The other thing is, a lot of things we think of as classic turbidite channels probably have a fair bit of benthic currents, moving stuff around. So I would actually posit that we've seen very few pure turbidite channels. That there's always going to be some water flowing around and rearranging things, and it's a spectrum, and we're humans. We like to split stuff up. We like to put end members, but in nature, Mother Nature doesn't know what we're thinking, so she's going to do what she wants to do.
No, that's interesting. And I think just the points you were making too about the changes across in facies across the drift. I know you did point it out, as simple as a net to gross difference across that drift, but just thinking of, as you're going through it, how much can we confuse that geophysically with something that might look a lot more sandy or might have more of an impedance contrast than we think over a broad scale. Just interesting to kind of place that in context when we're thinking of acting on some of these models, and and defining some of these as reservoir potential or trap potential. There's one more question that popped up, and then we'll answer this and then jump to a break. From Breno Goldenberg, how can we distinguish the point at which a reworked turbidite should be considered a contourite?
I would say, unless you see the classic Bauma sequence, if you will, or the typical supercritical flow bed forms, once it starts to flip over into anything that's larger scale than a ripple, that means you had persistent unidirectional currents going for more than a few minutes. You're talking about hours to get dunes organized, right? That's my flume experience in the old days. So so I think once you start to see things that are the decimeter scale cross bedding, and a lot of those we see the mud drapes and the bundles. So you're seeing evidence in these deep water deposits of the tidal modulation of the benthic currents that our first speaker was talking about. So.
Excellent. All right. Well, again, thank you for addressing those questions and a really good talk.